Now that we've gotten to the time value of money, we're going to talk about the specific model for this problem. So how did the time value thing? Did you hang on, stat?
Yeah, kind of. It was a lot of numbers, but I think I get it.
Well, good, because the spreadsheet is actually kind of complicated. So we're going to walk through it a piece at a time. Inputs, of course, were given in the problem. You go back and you can see that the down payment for the lease, the security deposit, the monthly payment, how many months is the lease, how much you pay per mile, what the limit is on miles, the end of the lease purchase price. We're all inputs. Then we have kind of the random parts, which we haven't randomized them yet. The mean, miles driven, and the distribution information for the interest rate. 8.5% mean with a standard deviation of 1%. And down here, if you buy it now, what the purchase price is. So there's some calculated fields. And this is still kind of in the inputs, and so I put it over here, but we could argue where they should go because it's not really an input, it's really a calculation. So if the miles driven is over this, then it charges 24 cents per mile. Otherwise, it charges nothing. So if they drive 20,000 miles, there's no mileage charge. And the car's value actually is the lease purchase price. And you'll notice over here, there's no charge for over mileage. If they do 50,000 miles a year, I probably need to fix that. There's a mistake. We can't have the car be negative. Oh, I put that in the wrong place. So there's the problem there. Sorry. 50. So there's a $4,800 mileage charge, also reducing the value of the vehicle by $4,800. And now there's a charge over here. We'll get to those in a minute. So that's how that works. We're going to fix this randomization part later. We want to understand the spreadsheet before we start randomizing things. Same with the interest rate. It's just a normal distribution, it says, but the mean's 8.5%, standard deviation 1. I just typed in 8% for now. So we need to change those. But that's what that value is. So what's going on over here? This is the more complicated part. Well, let's look at the cash flows. And these are nominal values. You have a down payment. So I'm just pulling it off of that value. You have a security deposit. You have 24 months of payments. The security deposit comes back to you at the end of the lease. And if there is a mileage charge, you have a mileage charge. But as we just spent in our little detour on time value of money, this is not the present value of these cash flows. These are the nominal cash flows. We have to compute the present value. So let's look at those formulas. This one's not that big of a deal because it happens now. The day you get the car, you make the down payment. The day you get the car, you make the security deposit. So they're actually the present value of those is the nominal value. The payments, this is where we talked about the present value function. Since it's a fixed amount for 48 months, so the nominal $10,992 of payments, the present value, the value today at 8% is $10,076. Same with the return of the deposit. You get the $550 back, but it's not actually worth $550 today. That's $550 2 years from now. Today, that's only worth $472. The mileage charge. We're saying if you drive 33,000 miles, you're going to pay them $720 at the end of 2 years, but that's the end of 2 years. Today, that's only worth $617. And I'm going to get the decimal places out of there because if you're making your car decisions based on dimes and nickels, you probably aren't making good decisions. But I want to look at these formulas, the different ways we did over here, the present value. This is using the present value function because it's a series of 24 payments. And I don't have the 24 payments laid out on the sheet. I didn't want to do that. Here it's a single value. So I did the essentially manual formula for the present value. It's the value divided by the interest rate raised to, in this case, 2 years. It's a monthly problem. So I did a 2-year calculation. So it's 24 months divided by 12. And I chose to do this in the interest rate. I chose to do it as an annual interest rate. I could have done this as a monthly interest rate, and I'll actually do the calculation over here so you can see the difference. It's not going to make much difference. It's a compounding area. But we saw on the time value detour, that money in the future, this is how you figure out what it's worth today. So the net present value, the present value today of all the cash flows as you sum those up. So we'll just do it with one of them. Actually, I think I prefer this view. What if I'd wanted to do it on a monthly basis? Well, it still would be H5 divided by 1 plus the monthly interest rate. So I'd have to take that rate and divide it by 12 and then raise to 24 months. If you look at the difference in the formulas, it's just where am I dividing by 12? And again, it's just changing the compounding. And it doesn't change the value by much. A little. Monthly compounding versus annual compounding does change the value. So that's a choice I made here. Back to idealizing and simplifying. I had to choose, am I going to do the mileage charge and the deposit return on an annual compounding or monthly compounding? I chose monthly or annual compounding. So if this is the interest rate and if this is the miles driven, the present value of the cash flows for the 2 years is $18,271. But then we have to decide how we want to model this problem. It's not clear in the textbook. Are we going to model this problem that we're keeping the car? If we buy it, we're just keeping it, which means we have to buy it at the end of the lease to properly compare buying versus leasing. Or are we going to plan that we're going to get rid of the car in 2 years, whether we buy it or lease it? It does change the calculation. So we'll start with the first option, that we're going to keep the car. So to compare the purchase price to the present value of leasing, I have to take these cash flows during the lease, and then I have to take the purchase price. Same issue. I know today that it's going to cost $29,732 at the end of the lease in 2 years, but that's not what that's worth today. That cash flow is not going to happen for 2 years. So I do the exact same calculation that I did for the deposit and the mileage charge. So all these values are now present value. So the total present value of leasing it for 2 years and then purchasing at the end of those 2 years is $43,762. And that is more than the actual true present value of just buying it today. Now the other option is that I would get rid of the car after the lease. I just give it back. But for a comparison there, then I have to compare that to selling if I bought it now. Well, we said that the future value is tied into this mileage just like the mileage charge. So in this particular example, if I drive it 33,000 miles, I can't sell it for $29,732. I can only sell it for $29,112. In a pure cash flow, a nominal value, that's the $43,240 I spent, minus the $29,012 I'll be able to sell it for in 2 years. But that doesn't take time value of money into account, because I'm subtracting a present value from a future value. To make that adjustment proper, to do it as a present value calculation, it does get a little uglier, but the present value for the purchase is still a present value. I don't change that, but what I get for it 2 years down the road, I have to do the present value adjustment. So even though we'll say it's $29,012 nominal dollars, it actually isn't that in terms of value because I have to wait 2 years to get it. So now if I'm going to get rid of the car, I compare the leasing cash flows and then give the car back to the dealer with the present value of buying it and then selling it for that value in 2 years. In both these cases, leasing costs more than buying. You'll notice it's not that far off though, especially if I keep the car completely. The keeping the car present values are remarkably close. Dumping the car in 2 years, leasing actually is quite a bit more expensive. And it's a working model. You could play the what if game. What if I drive 40,000 miles? Well, leasing still costs more. What if the interest rate is 10%? What if I only drive 20,000 miles? Well, there's a change. Now the lease is less if I plan to keep it. Getting rid of it, so far, it's still leasing is more expensive than buying if I buy and sell. So we do need to randomize this. So I'm going to pause. This is a place in the video you should stop. You should open this sheet if you don't have it open already, and you should go through these cells on your own and see if you can make sense out of these formulas. And I admit the present value calculation here is the ugliest formula in the whole thing, and I can't really fix that. That's how you do present value, but you should go look at it and see if you can figure out.
Looks like they're back. You need to wake up.
Oh, they're back? Do you think they really went away and looked at the spreadsheet?
I think they did. They're good students.
Okay. So now we've got a working model, but it's not a random model. This just lets you play what if. What if you drive a lot of miles or not so many miles? What if the interest rate is 10%, 8%, 9%? We want to do the randomization. Well, the normal we've done before. So I'm going to do that one first. We just reviewed it actually on the auction problem. So it's norm dot inverse of a random value with a mean of 8.5% and a standard deviation of 1%. So now every recalculation changes that interest rate. And what's kind of interesting, you may have noticed this playing around with it yourself, that if I'm just going to dump the car in 2 years, the lease always appears to be more than the present value of the lease. That's this value. It seems to always be more than the present value of buying it and selling it, kind of no matter what happens with this, and depending on what you did here, playing around with this. Now we got to do this one. According to the problem, it's an exponential distribution with a mean of 25,000. We did cover exponential distributions in the first simulation video, and if you have your book, you can look there. But if you have your book, page 200, Appendix 3, covers some of that stuff. You probably can't see it very well in the camera, so I'm going to put it up there anyway, just for fun. Page 200. It says to generate an exponential distribution, it's equal negative the mean times the natural log of a random probability. What exponential distributions tend to do, and if you play with this you'll see this after a while, is they're not symmetric at all like a normal distribution. They tend to bunch up towards the smaller values and occasionally have high values to extremely high values. So whether or not this is a good model for mileage driven is questionable. I mean, it's not likely you're going to lease a car and actually drive it 3,000 miles. But when you do a larger scale simulation, we'll see that it does what it does. So this is the problem they told us to use. So occasionally it gets very high. There's a pretty high one. But now we got what's really useful about a one trial simulation model. These decisions we're looking for. If I'm going to keep it, should I lease it now and then buy it, or just buy it? If I'm going to get rid of it, should I buy it and sell it, or just lease it? There's an interplay between these two values, because as they both change, the mileage changes this value, which changes this value, and the interest rate changes almost everything in this column. So they play into each other, which makes it very, very difficult to come up with a single mathematical solution for this problem. So again, we're not going to do the multi-trials yet, but now you actually have a working single trial simulation model. And then make sure you have that working before we come back to the next day of simulation, because this is another one. I gave you the start of this problem. I'm not going to give you the file with the randomization. So here's your chance to see it again. How do we do the normal distribution? Norm inverse, a random probability with this mean and this standard deviation. How do we do the exponential? It's the negative of the mean times the natural logarithm of a random probability. So make sure you get both of those working on yours before we go on to the next day.